sort of that threshold where the critical value goes from, failing to reject to reject. Okay, so that tells you the exact point. So it might be the case that at alpha equal 2.05, you reject. But let's say if we lower it a little bit, alpha equals 0.01, then you fail to reject that hypothesis. Well, then you know that your p-value is somewhere in between there. And so let's say we come up with a p-value of 0.035, and that tells us any alpha above 3.5% we're going to reject, and anything below it we're going to fail to reject. So it gives us that threshold. Okay, and so that should be pretty clear. This is the stuff we've gone over already. And so this is just with a single hypothesis test. So if we want to do a single hypothesis test whether some beta is different from some value, then we can do that. So what we're going to do today is talk about linear combinations of betas, or if we want to jointly test multiple betas, how do we go about and do that? And there's really three different ways that we can do that. And so this is still with a single restriction. We're still going to we're going to have some relationship, but it's still going to have a single restriction. And you can count the number of restrictions by how many equal signs you see will be the number of restrictions that you have. So here an example might be the following. So if we have, let's say, so this is going to be a multiple linear regression. And so we're looking at consumption as a function of income, or let's say salary income, investment income, and then family size. All right, so family gets bigger, you might consume more. We know that consumption of some goods is normal, some goods is inferior. Let's say we're dealing with a normal good here. But we might hypothesize that there's some difference between income that we get from salary and income from investment. All right, so we make, we get a pay increase at work. That could be different from sort of getting some money because the stock market moved in your direction one day. So we might want to test this to see if that is truly the case. And so the question here is the marginal rate of substitution different for salary and investment income? So is the impact is $10 extra in salary different from $10 extra in investment income? Okay, so we can write this hypothesis, in our normal notation. This is really what we're looking to test, right? Is beta 1 equal to beta 2? Is that marginal impact from x1 on y the same as the impact from x2 on y? Okay, so the null hypothesis is beta 1 equal to beta 2? Another way that you can write that is, and I think it'll be more helpful to think about it in this way, is beta 1 minus beta 2 equal to 0. Okay. So those two are the same things. Whereas our alternative would be that they're not equal to one another. Okay, so if we wanted to test this, there are 3 different methods we can use to test that. Okay, and really these three ways of testing are equivalent. They're all equivalent. They're all going to give you the same results. Some are just going to be easier than others. Okay. So the first method is to just basically do a t-test, right? So you have construct a new t-value, beta 1 hat minus beta 2 hat minus 0, and then divided by the standard error of, right? Isn't that kind of what we're looking at? So the standard error, beta 1 minus beta 2. So if we had some value that was the difference in beta 1 and beta 2 hat there, and then we assume that that is distributed as a t-distribution under the null hypothesis. So, we can calculate our t-value, we can look at our critical t-value, compare them, and get that. The reason this is not as easy as it seems is that, right, this top part's pretty easy. We can estimate beta 1 hat and beta 2 hat pretty easily. It's this variance part down here that's going to be a lot of fun to compute. But actually, we can calculate that. That's no problem either. It's just going to take some work. So we know that if we have something like this, so we know we can calculate something like that if we just calculate the variance. And we can actually do something like that. If we use in SAS, so this is in SAS, we can use this, procreg model x1, x2, and then a backslash cov b, and run. So what this will give us is a covariance matrix for beta 1 and beta 2, where this variance of beta 1 will be the element, right? So it'll be a matrix with 4 elements. That'll give us. And so the element up here will be the variance of beta 1, and then the element down here will be the variance of beta 2, and then the covariance will be right down here. So we can actually do this in SAS. It's just a matter of printing it out and then doing this. And then we just we recognize that the standard error of beta 1 minus beta 2 hat is just equal to the square root of that variance. Actually, you should all pass on that. Okay, so we download our data. We run procreg. We use this command right here. We print out the covariance of B. We can obviously calculate the top of this t statistic, right, with our estimated parameters. And then the bottom we can calculate just from this covariance matrix. We can get that as well. You know what? Let me see if we do it sense. And then we compare that to the t-value that we calculate, and so just like a regular t-test, we can reject or fail to reject that hypothesis. So that's kind of the first method, and you can do that with anything. All these methods you can do anytime you have a single parameter restriction, right? No matter what the linear function is. So if this were beta 1